So back with another video. I'm actually not at my home location, so it's not going to be that good. But the information, this is a new topic for me, and I'm really interested in it. So we're just going to get right into it. Your CPU is broadcasting what it's doing right now through heat, power draw, and even the timing of its math. And none of that shows up on any log file. By the end of this video, you'll understand the physics behind Spectre, Meltdown, and power analysis attacks, not just what CVE number, but why they're even possible at a hardware level. This video is where electrical engineering and hacking stop being two different subjects. The problem: transistors aren't perfect wires. Every wire on a chip is packed nanometers away from its neighbors. At that scale, wires aren't just on/off, they behave like tiny capacitors and antennas. Defining parasitic capacitance: any two conductors separated by an insulator store a little bit of charge between them. Whether you design it or not, on a chip, the insulator is the dielectric material between metal layers. When one wire switches state from 0 to 1, the changing electric field induces a small unwanted voltage on the wire next to it. Like an example here is like two guitar strings vibrating in symphony. I don't think that an electric field inducing a small unwanted voltage on the wire next to it really needs an example like that. I think it's pretty easy to understand. Crosstalk is the same phenomenon that causes interference between adjacent Ethernet pairs, which is why twisted pair cabling exists. Twisting cancels out the induced field. Chips can't twist their wires, so they fight this problem differently. Shielding, spacing, low-K dielectrics. Why chip makers care? Low-K dielectrics. As transistors shrunk, wires got closer together, so parasitic capacitance and crosstalk got worse, not better. Dielectric constant, K, in plain terms, it's a measure of how well a material lets an electric field pass through/store energy. Higher K equals more capacitance for the same spacing equals more crosstalk and more delay. Chip makers moved from SiO2 towards carbon-doped glass, porous materials, etiquette. Low-K dielectrics exists specifically to reduce this parasitic capacitance, so chips can keep shrinking without crosstalk destroying signal integrity. This is one of the main reasons modern CPUs can run as fast as they do. Managing unwanted capacitance is a first-class engineering problem, on par with raw transistor speed. For example, I guess, a side channel attack doesn't break your crypto, it listens to the physical footprint of your crypto, power draw, timing, electromagnetic emissions, and reconstructs the secret from that footprint. The same imperfect wires that make your CPU leak crosstalk into itself also make it leak information out of itself. Now, what if this leakage that's getting out is actual information that could jeopardize you in some way, shape, or form? Everything above is a signal integrity problem to a chip maker. To an attacker, it's a side channel and unintentional output that correlates with secret internal state. Now I'm going to talk about three real world examples. Timing attacks, power analysis, and then we have Spectre, Meltdown. Spectre/Meltdown. They're not together. Spectre Meltdown, I believe, was some vulnerabilities in CPUs in 2018. So the first one, timing attacks. These go back to my own day 3 lab, which was the last video I posted, pretty sure. The Flask login timing lab, string comparison. The string comparison took microseconds longer per correct character. Same principle, just software level instead of hardware level. SPA, simple power analysis, DPA, differential power analysis. Conceptually, a chip doing AES draws a measurably different amount of power depending on its bits. Depending on the bits, it's processing because different transistors switching patterns draw different current. This connects straight back to the parasitic capacitance. Charging, discharging those unwanted parasitic capacitance is literally where a lot of that power draw variation comes from. Later in this series, I will actually measure this with a $15 USB-C power meter. And I'm going to make a video out of that, so that'll be cool. That fingerprint is measurable purely through timing, just exploiting the memory hierarchy instead of a login form. So why this even matters as a red teamer? I mean, you can kind of tell by now, like, if you heard, it's literally leaking information. Side channels rarely show up in a standard in-map GoBuster Metasploit workflow. They live below the application layer entirely. Worth knowing they exist, even if you're not exploiting them. So basically, this will be a series, and next we will extend the timing attack lab to network level timing, then measure real power draw, side channel attacks ourselves, then visualizing RF emissions with an SDR. Subscribe for the next video. May or may not be timing attacks part 2. Drop a comment on what you want explained deeper, and Grease to Root signing off.